Hello, this is Yang Ge. In this tutorial, I'm going to talk about graph-level optimizations in the ONIC framework. This is the outline. First, we will introduce the graph-level optimizations that are currently supported in the open-source ONIC. After that, there is a lab section that demonstrates how we can add a customized optimization path under the ONIC framework. When we talk about graph-level optimizations, we mean those optimizations that manipulate ONIC IR graphs. More precisely, this kind of optimization takes an IR graph as an input and yields another IR graph which is functionally equivalent to the input. These optimizations come for various different purposes. A majority of them are to simplify IR graphs by either removing redundant nodes, fusing multiple nodes, or refactoring certain operator. For example, we have dead node elimination that removes the nodes whose outputs are not used by any other node. As shown in the figure, operator C only has one output, tensor C, which is not used by any other node, so it will be removed in dead node elimination. One example of layer fusions is eliminate cast. In eliminate cast, if a cast operator follows immediately after an initializer, then it will be merged into that preceding initializer. To simplify the logic of later implementation, we might sometimes refactor certain operators. For example, batch normalization is actually equivalent to an addition with a constant followed by a multiplication with a constant. So in ONIC, we just convert any appearance of batch normalization to an add operator and a multiply operator, so that we can avoid duplicated logic in code emit stage. Some operators are added in order to get rid of operators that are not supported in the target backend. We achieve this by converting them into some other supported operators. For example, NVDLA cannot support a pooling operation where the kernel width or height is greater than 8. So in general, global average pool is not directly supported on NVDLA. Most of the time, we would have to convert it into several average pools with sufficiently small kernel. Depending on our target backend, there may also be some hardware resource constraints that we have to meet. Like in NVDLA, the size of the convolution buffer is limited. So when we have a convolution where the input size is too big, we can only do convolution on partial input at a time and accumulate the results. The above are just a few of the optimizations we have. In the open source ONIC project, we currently support 10 optimizations in total. This slide is the list of all of them. Feel free to add more according to your needs. Here we come to the lab section. In this lab, we'll show how to create an optimization path and add it to your backend. The figure illustrates the optimization we are going to create. It's called eliminate no up transpose, meaning that it removes all transpose operators with identity permutation. These transposes actually do nothing, so we can simply remove them. This is an overview of our workflow. First, we will implement a new path using the custom path template. After that, we will add the path into our target backend. And finally, the path implementation files. We add the path implementation files into the building system of ONIC. Now we demonstrate how to implement an optimization in detail. The header of a new optimization path may look like this. We define a new class derived from custom path and override run-on-module method. In an optimization path, the return type of run-on-module basically indicates whether there's any change to the IR graph during this path. Taking our eliminate no up transpose, for example, if the input graph has no such kind of transpose that we are looking for, then it will remain unchanged after the pass. Otherwise, some node will be removed from the graph, and in that case, run-on-module should return a module change verdict. In the ONIC framework, there may be multiple graphs in a module. Most optimizations don't need to refer to all compute graphs as a whole, but only look at one compute graph at a time. So this shows how a typical random module looks like. We iterate through all compute graphs in the module and do our work for each of them. This shows a possible implementation of eliminate no-op transpose on a single compute graph. The first section collects all trivial transpose operators to a list. The second section shows some important routines required when you want to make some changes to an ONIC IR graph. One thing is that when we remove an operator from the compute graph, we should also remove all its output tensors, because conceptually, these tensors only exist when its producer exists. In this case, out v is the tensor that's going to be removed along with the node. After the removal, all operators that originally takes out v as an input will use in v instead. This can be done by using the replace all users with API. The purpose of this remove all inputs line is to remove no-op transpose operator from the user list of inv. Finally, the no-op transpose node and out v is erased from the graph. Now we are already done with the implementation of a new optimization path. To add this path to your backend, you just need to include its definition header and add a path to the path manager. Note that according to our framework, any graph level optimization should be added in this add ONIC IR optimization block. Finally, add your implementation file to the CMake list under the same directory. And that's all we need to do to create a customized optimization path. To make it easier to see the effect of our optimization, we also introduce a visualization path. This path dumps the current compute graph in GraphViz format, which is a language supported in Markdown that can be used to render an image of a graph or network. What we will do is insert this path after our new optimization so that we can see how the graph changes. We do not elaborate on the implementation of this path, but the workflow is quite similar to the previous one. This is the demo section. Now we are in the open source ONIC repository. In this demo, we have prepared an ONIX model where there is a trivial transpose operator. So later on, we will test our new compiler on this model. First, we can check out how this model looks like. We can see that there are two transpose operators in this model. The first one after x1 is a trivial transpose operator. It does nothing, so in our new optimization, it will be removed. The other transpose after x2, it actually swaps the last two dimensions, so in our new path, it is not supposed to be removed. Now we go into our target backend. In this demo, we will show all our work in the NVDOA backend. This is the list of all we have to do in the lab. We have two new passes. In the previous slides, we have already gone through all the details of eliminate no-op transpose. Now we can take a quick look at the graph visualization pass. This is the definition header. We can see that it is pretty much the same as eliminate no-op transpose. We derive the new pass from custom pass and override random module method as the entry point of the pass. The implementation is also quite similar. We iterate through all the compute graphs and do whatever we want in each iteration. One thing different is that since this is a visualization pass, it does not change the graph at all. It will not add any node or remove any node. So every time it is run, it returns a module no change verdict. Now we already have the definitions and implementations of the two new passes ready. The next step will be to add them to our target backend. Adding a pass is actually quite simple. We just include the definition headers and add them to the pass managers in this add ONIC IR optimization block. Note that we add the graph visualization pass after the optimization so that it will dump the graph where all the trivial transpose operators has been removed. The final step is to add our implementations to the building system. And this is also quite simple. We just add those CPP files to the CMake list of our target backend. So that's all we have to do to add new optimizations. Now we can go to the ONIC Docker container to rebuild the compiler. If you have already built the compiler in the same container previously, then the rebuild is supposed to be very fast. Now the rebuild is finished, and now we can test the new compiler on our prepared model. And it works. It dumps the IR graph in the GraphViz format. To see how this graph really looks like, we can just paste it on a Markdown node. So here it is. We can see that the trivial transpose operator after x1 has been removed, but the other one after x2 remains there because it is not a trivial transpose operator. Alright, so this is the end of the demo section and also the end of the tutorial. Thank you.